All right, let's talk about removable discontinuity, or what we call holes in a graph, and vertical asymptotes. We've talked about the parent rational function y equals 1 over x, but what do we do when we have a rational function with variables in both the numerator and the denominator? So this is what we're going to do every single time. I want you to take your function and factor the numerator and the denominator individually as best you can. Look for a GCF, look for the difference of squares. Are you factoring a trinomial? Whatever it is you've got to do, factor it all the way down. And then once you do that, I want you to look for common factors between the numerator and the denominator. And in this problem, we have x plus 2. So once you find a common factor between them, you set that common factor equal to 0 and solve. So when we set x plus 2 equal to 0 and solve, we get x equals -2. That means we have a hole that exists in our graph when the x value is equal to -2. Now, if you were to graph this on a calculator or on Desmos, the hole is so small that you wouldn't actually see it. So you do need to understand this rule because the hole does exist there. It's called removable discontinuity, okay? Now, we also have vertical asymptotes. So after you've factored and you've found holes in your graph, you are going to take any remaining factor in your denominator, only in your denominator. So I look right here and I see x minus 2, and I set that equal to 0 and solve. Well, that equals +2. X equals +2 is your vertical asymptote. So you still have that imaginary boundary line that your function gets really close to. So now that you found your holes and vertical asymptotes, those are your domain restrictions. Those are your domain restrictions. What's a restriction? Something that you cannot do. So our domain is just the set of all x values such that x cannot equal the -2 or +2. So whatever values we got for our holes and our vertical asymptotes, those are the domain restrictions. So every single x value is allowable, just not these two numbers. And that's it. So let's do a couple of practice problems really fast. So this first example is y equals x squared minus 16 over x squared minus x minus 12. And again, you need to know how to factor in order to find the attributes of these functions. So if you don't remember how to factor, go back and watch some of the factoring videos, okay? So x squared minus 16. I can see that this is the difference of two perfect squares. Difference is subtraction. X squared and 16 are both perfect squares, so this factors into x plus 4 times x minus 4. And then in our denominator, x squared minus x minus 12, there's no GCF there, but I can factor this trinomial. The factors of -12 that combine to give me a -1 are x minus 4 times x plus 3. So that's our factored form. Guess I should have put that over here, huh? Where it says factored form. That's the factored form of our function, right? Now, in this case, I need to always look for removable discontinuity first, or holes in our graph. So where do I have common factors in my numerator and denominator? And I see that I have x minus 4. So I take x minus 4 and I set that equal to 0. And then I solve for x. X equals +4. That is where we have removable discontinuity. Now I look for a vertical asymptote. Whatever remaining factors are in my denominator only, I set those equal to 0. So I set x plus 3 equal to 0, and then I solve for x. Well, x equals -3. That's where we will have a vertical asymptote. So the domain for this function is the set of all x values such that x cannot equal, and we're going to use these two values, and we always list from least to greatest, -3 or +4. All right? All right, let's do one more example. We have y equals x squared minus 4x minus 5 over 3x squared minus 75. So let's factor that. If I look at my numerator, x squared minus 4x minus 5. The factors of negative 5 that combine to make a negative 4 are going to be x minus 5, and we've got a plus 1. So there are the factors of our entire trinomial, right? X minus 5 times x plus 1. Now the denominator is a little different. It says 3x squared minus 75. I see that I only have two terms. We have a binomial and it's a difference. So I want to know if this is the difference of two perfect squares. Well, 75 and 3 are definitely not perfect squares. But I do see that both of those terms are divisible by 3. So let's go ahead and factor out the 3 first and see what we're left with. X squared minus, and then 75 divided by 3, think of 75 cents. That's 3/4. A quarter is 25 cents. So we have x squared minus 25. 3 times x squared minus 25. Oh, wait a second. X squared and 25 are both perfect squares. So let's go ahead and factor that. That's the difference of two perfect squares. We bring down the 3. And this becomes x plus 5 times x minus 5. So we have 3 times x plus 5 times x minus 5. All right, so now our removable discontinuity. Let's see if we have any common factors between the numerator and the denominator. And I see they both have an x minus 5 factor. So let's set that equal to 0. X minus 5 equals 0 gives us x equals 5. We have a hole in our graph when the x value is equal to 5. And now we look at our denominator and set any remaining factors equal to 0. We have both a 3 and an x plus 5. So ask yourself, does it make sense to say that 3 equals 0? Definitely not, so that's not going to do anything for us, but x plus 5 can equal 0. And when we solve for x, that gives us x equals negative 5. So we have two domain restrictions. We have a positive 5 and a negative 5 here, right? So this is just the set of all x values such that x cannot equal negative 5 or positive 5. All right? And so that's how we find removable discontinuity and vertical asymptotes for our domain restrictions. Now in the next video, we're probably going to talk about horizontal asymptotes, and those are super fun also.